Okay, welcome to the third part of our functional mockup interface in industry series. I want to show you today something about co-simulation and what this is and how this works in general. So, you remember maybe we had this Euler forward integrator system in the last video where I just want to remind you this was an iterative solution to solve ordinary differential equations, and there were some numerical errors involved. Yeah, I know. We start with this basic principle that we have integrators, and now we go into co-simulation. So this is the pre-step, what we need, this general integrator principle to understand the co-simulator. Let's recap. Okay, we have computational time to the right. That's the time that you feel while you sit in front of your machine, whatever this means. Then you have one process. You do one step at a time. For example, one Euler step forward. And after you did that, you have a new situation, you have a new state. You do another step and another step and another step and so on and so on. And by appending these steps one to each other, you get complete integration results. So this is the single step non-co-simulation stuff, so to call. Just to repeat that. Now let's get into the co-simulation. In co-simulation we have multiple processes running in parallel. So I call them now process 1 and 2. It could be 3 or 4 or more. It doesn't matter. We have more than one. And what we have there is a macro step, which is 1.1, because it's the first macro step of the first process. That is, in fact, just some integration that's done on one part of the system on one process. I'll come to that in a second. Parallel, so you need multiple cores to do this efficiently. There is another macro step involved. The 2.1 is on the second process, ideally on the second processor, on the second core, or could be on a different machine even. But what you get is that those two macro steps are running in parallel. Now what's important here is there is no information exchange between those two while they are running. So only after successful integrating both steps, there is, for one, the information of the result of the first process being transferred to the second process and vice versa. So there is a communication step, and then you can do the next macro steps. And again, communication. So you get the rough idea. So this is very similar in some sense to the Euler forward, but it has a significant difference because such a macro step, just here at 2.1 shown, consists of multiple, doesn't matter how many, individual steps. So you could use, for example, your Euler forward to do such a macro step, but this macro step is not just one step in the Euler, but might be 100 or 1000 steps. This is okay, this is perfectly fine, because this process runs for a certain time and then it resyncs with the other processes. The shorter this macro step is, the more communication overhead you generate. And if this is over network, for example, then you see this is a penalty, so to call. Okay. In classical integrators, you have the complete state that you know and you have in your RAM, more or less. So you can do arbitrary, what you call random access to whatever variable you want to have. You are not restricted in any case. In co-simulation, on the other side, you separate and you segregate your simulation model into parts, and this synchronization becomes crucial, because only at the points of synchronization you can actually see the complete model, and otherwise you only see part of your model. And generally speaking, and this is no hard statement here, it's not always suitable, but it's good for loosely coupled components. So if you have two components that are tightly coupled, then the co-simulation will break more or less for sure. While with loosely coupled components, you have a good chance that each of them can run their individual simulation and then only at the synchronization points be synchronized and keep in track more or less. So I give you an example, and this is a rather strictly coupled system. This is just an oscillator. So we put this x1 dot is x2 and x2 dot is minus x1, which is just classical oscillator, and the solution is also pretty straightforward because it's just sine and cosine for x1 and x2 depending on the initial conditions. And now let's look at this in the sense or in the context of co-simulation. And what we want to do is we want to do some co-simulation. We want to do a communication interval at 0.3, which is just arbitrarily chosen. So each 0.3 time intervals or time units, there will be a communication, otherwise there will be no communication. And we will obviously segregate the model by x1 and x2, so the left column is one process and the other column is the other process. So we see on the bottom side these plots that we will build soon. But in contrast to the Euler, where we know everything in one machine and have access to all state and blah and blah and blah, as I already mentioned, we have some difference here because each of these states have their individual derivative. So we need to keep in track that the derivative of x1 is x1 dot and for x2 as well. And the important thing is that we have now changed our differential equation a bit, because it's no longer here x1 dot is x2, but x1 dot is x2 hat. x2 hat and x1 hat is nothing more but the estimation due to this communication delay, or it's not really a delay, but it's even a discretization. And the hats, x1 hat and x2 hats, are these quantized and discretized values of x1 and x2. Let's have a look at how this works. So we know initial values are there, so we have 2 points. We know this principle that you have some values and you construct the rest is very similar to the Euler forward. So if you don't understand it, go back to the Euler forward. There it's more explicitly explained. So let's start from here. What we can now do is, first thing, we can do some communication. Okay, fair enough. So we know x2 hat can be initialized with x2 and x1 hat can be initialized with x1. So we know the values can be transmitted. But yeah, that's that. We stop communication. And the question is, if you look at x1 on the left process, more or less, how will x1 dot behave over time? And we have no communication, so we don't know. There is nothing really we know of x1 dot, because it would be the other system. So the best thing we can do is just give a good guess. And the best guess we so far have is we say, okay, we had this value before, so 1 and 0, and yeah, we keep that value at that level. So x1 dot is kept at 1 and x2 dot is kept at 0. This means we have now a trajectory for the derivatives of x1 and x2. Means we can use classical integrators to actually compute the state trajectory for this short period of 0.3 time units. So doing that, we get the next time span, and the difference to the Euler forward is this is actually integration. So if we had a better estimate, because there was not only a constant in the derivative, but it would be some arbitrary function due to whatever magic we did there, then this would not be just a straight line like in this example, but it would be some curve with some curvature. This is fine for co-simulation because these steps are much larger than the steps an Euler, for example, would take. Okay, now we have the next point in time where we have communication allowed. So we again do some communication. We put the next information in the derivatives, and what we will get is again just an estimation for the next 0.3 time units. So we have again the derivative known and can integrate the state. And we redo this and finally get some solution. I skipped here over, and if we compare that with the optimal solution, which is this green dashed line, you will see there is also some error. And this error comes from the fact that we had here just estimated the derivative with a constant, with a piecewise constant function, and you see in the upper side that this is for sure not true. This is for sure not the correct value, and therefore the integration will create some errors. It will not fail completely, but it will create some errors. And this is the point where co-simulation creates problems, or can create problems. So now you understood, hopefully, this principle of co-simulation, and you should be able to transfer your knowledge about the integrators here in this context. This was it about co-simulation. Now you should have understood the principles, and you should be able, with the knowledge about classical integrators, how to read this and how to get a grasp on this. This is the part so far. So next is the FMI part. We'll go into the introduction first, then some more in detail stuff about FMI, some implementation even later on. And I hope you will join the next videos as well. See you soon.